In the current lecture, we are going to discuss a very important concept of quantum statistics, and this is regarding density matrix. Actually, this density matrix is just a classical analog of the density distribution function. You have studied in the earlier lecture the density distribution function denoted by the symbol rho, which in general is a function of the position coordinate q, the conjugate momentum p, and probability time t2. In case of a stationary system, this time is not present here. So this is actually called density distribution function or probability distribution function. This density matrix is actually the classical analog of this density distribution function. Okay. As the name states that this will be expressed in terms of a matrix, and you know, actually in quantum mechanics, all the quantum mechanical operator are expressed as a matrix. We can express a quantum mechanical operator in matrix form, and so that actually this density matrix is actually a quantum mechanical operator, and that's why this operator is also called a statistical operator, or it is also popularly known as density operator. Okay, and as I have told you that this is a very important operator used in solving the quantum mechanical problem. So actually this density matrix, you can say, is a powerful and versatile tool for describing and analyzing the statistical behavior of quantum mechanical system. Okay. In fact, this formalism of density matrix allows us to calculate the various properties of quantum system, and among those various properties, I have mentioned here some of the important properties that can be dealt, that can be described, that can be analyzed, or that can be evaluated by the use of this very important operator, which is called density matrix. Let us see what are the important applications where this density matrix can be used. You can use it to find the expectation values of observables. You can also use it to find the ensemble average, evolution under time dependent Hamiltonians, calculation of entropy, and entanglement measures. Okay, these are some of the important applications where this density matrix finds its application. Okay, now actually this density matrix, you know, is a quantum mechanical operator, and most of the quantum mechanical operator, you know, are Hermitian. So actually this density matrix is also a Hermitian operator, and actually this Hermitian operator is positive and semi-definite matrix. Okay, and you know that in quantum mechanics we always define any operator in terms of the associated wave function or the state vector or the eigenvector. So actually this density matrix is also defined in terms of the state vector, or you may call it eigenvector or wave function psi. Okay, now as you know that quantum mechanical system may be in two types of states. The first one is called pure state, and the another is called mixed state. While you are talking about the statistical mechanics in general, we will talk about the mixed state. Actually, this pure state in general is a theoretical concept. Normally, our system or quantum mechanical system are found in general in mixed state. Pure state is just an idealization. But theoretically, we will consider this pure state too. So we will define this density matrix considering our quantum mechanical system in pure state and also in mixed state. Okay, so let us see how this density matrix will be defined when the state of our quantum mechanical system will be a pure state. When you say that a quantum mechanical system is in a pure quantum state, what does it mean? Actually, a pure quantum state of a system is represented by a single eigenvector or a state vector. Let us say that single vector is psi alpha. Actually, alpha is just an indication of the state. You can say that our system is particularly in a state denoted by this kate alpha. This is a single state. So if the quantum state of our system is represented by this single state vector kate alpha or psi alpha, then you can say that various state of the system is a pure quantum state. Okay, and if a system is in a pure quantum state, then how this density matrix is defined? The definition is very simple. Actually, in this condition, the density matrix is simply the outer product of the state vector with itself. It means if this pure state has the state vector psi alpha or kate alpha, then you have to take the outer product of this kate alpha with itself, and that will give the density matrix of that pure state. So if we denote the density matrix by the symbol rho, then rho is simply equal to outer product. This is just outer product. Actually, this sign here has touched one another, but mark this symbol like this, that these two angle brackets are actually not touching one another. Okay, so you can see, or I am just erasing that symbol. You can see. Okay, now see here, this is like this. Okay, and this is this is the symbol of outer product. So when our system is in a particular state denoted by the state vector kate alpha, then the density matrix is equal to the outer product of kate alpha with itself. And so this equation 1 defines the density matrix when our system is in a pure quantum state. Okay. Now we will see the case of mixed state. One thing here I have mentioned that actually when the system is in a pure quantum state, then density matrix you can see is just an outer product of the state vector with itself. So in this case you can say that this density matrix is a rank 1 projection operator. Actually, when we take the outer product of two state vectors, we get a projection operator. So in this case, density matrix is simply interpreted as rank 1 projection operator. Okay. Now we consider that our quantum mechanical system is in a mixed state. It means there are so many systems, you can also say, and and the state is not pure, but it is just a combination of different quantum states. In statistical mechanics, there is a very good example of this mixed state, and this is a statistical ensemble. Okay, so I have mentioned here that a mixed state is described by a statistical ensemble of different pure states. Okay, you can consider that there is a large number of pure states in the ensemble, and so that is called a mixed state. Okay. In fact, when there will be a combination of different pure states and our aim is to define or find the density matrix, how we can find? Actually, you have to take the outer product of the different pure states. let us consider that our different pure states are Kate, Kate I, Kate J, okay, Kate K, and so on. Okay. In this condition, if your aim is to find the density matrix, what you will do? We will actually simply find the outer product of the different pure states with itself and multiply them. So, and sum of them, not multiply. So you can write it like this. This is outer product of I, sorry, this has been just written wrongly. So see here, outer product of Kate I with I plus outer product of J with J plus so on. But one thing here is also remarkable, that what is the probability of a particular state? In fact, our system may be in different quantum state, but the probability of finding of the system in different quantum states will be different. So actually we have to take in this condition the weighted sum, not the simple sum. Okay. So let us consider that the probability of finding of the system in this particular quantum state denoted by the Kate vector I is, let us say, P of I. Then you have to multiply this outer product by Pi. So finally you can say that in the case of mixed state, the density matrix is actually a weighted sum, not the simple sum, of the outer products of the state vectors of the different pure states. Okay. And so let us consider a statistical ensemble with probabilities P of alpha, for which each pure state is Kate psi alpha, or you can say Kate alpha. In this condition, when we will sum up the weighted sum of the outer product of different pure states, what will be our result? You can see that will be sum of P alpha times outer product of psi alpha with psi alpha, or you can say that this is sum of the outer product of P alpha times outer product of Kate alpha with Kate alpha. Okay. So rho is in fact in this condition defined as sum of P alpha times outer product of Kate alpha with Kate alpha. Okay. So in this way, in case of mixed state, we can find the density matrix. Okay. Now actually when you talk about the state vector psi of alpha, which is for a pure state, you know that actually a state vector psi alpha, which represents a pure state denoted by the symbol Kate alpha, that can be expressed as a linear combination of the orthonormal eigenfunctions phi n, different phi n. So you can write this psi alpha is equal to sum over n Cn alpha times phi n. Okay. And if you will take the complex conjugate of this psi alpha, you can write psi alpha star equal to summation over m Cm alpha star phi m star. Actually here I have changed the index n to m. This is just a state change. Okay. And actually these Cn or Cm are actually the coefficient of expansion of this psi of alpha. Okay. So as this psi of alpha, which represents the eigenvector or the state vector of a pure state, are expressed in terms of the linear combination of the orthonormal eigenvectors phi n, So in this condition, from by the use of this equation number 2, if your aim is to find rho, what will be the result? In this condition, now we write rho as rho mn. Okay, this is actually m by n matrix, so the components are written here in by the symbol rho mn. And this rho mn will be now what? At the place of psi m of alpha, psi alpha star, you can write this p alpha times cm alpha star, and at the place of psi alpha we will write this cn alpha, okay, times this. And so this is the scalar product of this phi m star and phi n, okay. But you know that this phi n or phi m are orthonormal. These are here the sign will be like this. Now, since phi n is an orthonormal eigenvector, so this outer product will be simply equal to 1. Okay, this will be equal to 1. And so I have omitted it, and you can write that this rho mn is equal to sum of p alpha times cm alpha star cn alpha. And this is actually the basic definition of the density matrix in case of the mixed state of our quantum system. Okay. Now we will see some of the important properties of this density matrix. So the first property, as I have told you earlier, that this is just a Hermitian operator. So this density matrix is an operator, and this acts on the Hilbert space of the system. Okay. Now, as you can see that this matrix has been expressed by a m times n matrix, so its components can be written like this. This is rho 1, rho 1 1, rho 1 2, so on rho n, and similarly rho 2 1, rho 2 2, rho 2 n, and in this way you can write rho m1, rho m2, so on rho mn. Okay, in most of the cases this m is equal to n. Okay, actually the diagonal elements of this matrix, these are the diagonal elements. The diagonal elements of this density matrix provides information about the probability of the system being in a particular state. Okay, what is the probability of the system of finding in a particular state? That is determined in terms of the diagonal elements, while the off diagonal elements of this matrix contain the information about the coherence and quantum correlation between different states. Okay, different states. Now, as I have told you that it is a Hermitian operator, and as you know that any Hermitian operator is self-adjoint. So you can say that this rho mn is equal to rho mn dagger. This is its Hermitian conjugate, or in other words you can write rho mn equal to rho mn star. Okay, as I have mentioned earlier that it is positive and semi-definite. When you say that density matrix is positive and semi-definite, what does it mean? It means that all of its eigenvalues are non-negative. All of its eigenvalues are non-negative. And when you will take the trace of this density matrix, what do you mean by trace of the matrix? Trace of matrix means sum of these diagonal elements. So when you will take the sum of the diagonal elements, you will get the trace of this density matrix, and actually the trace of a density matrix, that is sum of the diagonal elements of the density matrix, is always equal to 1. Actually, this result implies the normalization of probabilities. Okay, normalization of probability. So, in brief, I have described the meaning and the important properties of this density matrix. But now, in the further lecture, we will see first of all one of the important applications, that is the time dependent time evolution in this application. I have mentioned it here. You can see we will discuss particularly this application, evolution under time dependent Hamiltonians. Actually, when we will consider this application, you will get a very important result, which is also known as quantum mechanical version of Liouville's theorem. So in the next lecture we will see the time evolution of Hamiltonian or time dependence of Hamiltonian, or in other words you can say in the next lecture we are going to deal with the quantum mechanical version of Liouville's theorem. Already we have studied its classical version in the previous lecture. Okay, thank you very much.